I'm going to be covering the theory of standing waves in a thin rod as well as in open and closed pipes together. On the left side, I have a rod that's clamped to one end and the other end is free to vibrate. So this end is attached to some wall, for example. Or you could have a pipe, like an organ pipe, with one end closed, while the other end is open to the atmosphere. On this side, I have a rod which is free to vibrate on either end, but the middle part is clamped. And also I have an open pipe, a pipe that's open on both ends. Think of a flute. It's open on both ends. So now what I'm going to try to do is to show you what kind of waves can develop in each object. Since it's easier to draw the waves in a container, I'll use the container approach, but the basics are going to be the same. Let's ask what kind of waves can possibly result. You have to never have any vibration on this end because it's clamped, so that's got to be a node, which I'll call N. And on this end, you have to have an antinode, which means there's going to be a maximum vibration on that end. I'll call it AN. Similarly, for the pipe with one end closed, you have to have a node on this end and an antinode on the open end. Here, it's going to be AN. The middle has always got to be a node because it's clamped, and an AN. Now this one does not have any restrictions on what it can be in the middle, but it has to be an antinode on either end. So let's see what patterns will result. The theory for these two will be identical, but the theory for these will not be identical. In fact, there will be always more modes for the pipe that's open on both ends than for a rod clamped in the middle. The rod clamped in the middle will rule out any mode that occurs here which has an antinode in the middle. So if I do this one first, it would be beneficial because then I can simply pick out the modes which will be suitable for the rod that's clamped in the middle. So I'll do this one first, and then I'll pick every alternate one because only the ones with nodes in the middle will suit the purpose for the rod. Here, both of them will be identical. So let's proceed to actually find these various modes. I'll start by drawing the mode diagram on the left end. I think I'll do 3 of them and the pattern will become very clear by the time I finish the third one. The simplest possible mode that you can fit in would be that. Now that is 1/2 of a melon, and each melon is half a wavelength, so that's lambda 1 over 4 because it's half a melon, and that's equal to the entire length, which I'll take to be L. This is the length of either the rod or the pipe, which means that lambda 1 is 4L, which I'll write as 4L over 1. You'll see why I'm doing that. The next possibility is for us to have, this end has always got to be an antinode, so the only way that can happen is if there's a node somewhere here. So you'll get a tadpole-like wave. Well, that's got a lambda over 2, which is a full melon, plus half melon. So lambda over 2 plus lambda over 4, and that's 3 lambda over 4. I'll call it 3 lambda 2 over 4 equals L. And that means lambda 2 is equal to 4L over 3. When I say 2, I mean the second thing that occurs. But it might be probably better for me to call this lambda 3 in view of our final result, because this 1 and 1, 3 and 3 will match up. Okay, the next mode will be one where you get this, and that's going to be 1 full lambda plus a quarter lambda, and that's 5 quarters lambda. I'll call this lambda 5. And so that gives me lambda 5 equals 4L over 5. So this result is sometimes summarized in books, for example, by saying that only the odd harmonics will occur in either a rod clamped on one end or a pipe with one end closed. And the odd harmonics are given by lambda n equals 4L over n, for n being an odd number, numbers like 1, 3, 5, 7, and so on. Let's move on now to the theory behind the pipe that's open on both ends. And like I said, we'll select from that a subset that applies to the rod clamped in the middle. So the simplest possibility here is that you have this. Now that's a quarter melon plus a quarter melon, and that makes a half melon, which is half melon plus a half melon, which makes a full melon, and that's equal to a quarter half wavelength. So lambda 1 over 2 equals L. So that gives me lambda 1 equals 2L over 1. This will also be suitable for that because there's a node in the middle. So that applies to both cases. Let's try the second one. Now this time I'm going to have two of these nodes, and you can already see that this is impossible to have for the rod clamped in the middle, because the rod clamped in the middle has to have a node in the middle, and this has an antinode in the middle. So this mode will only occur in the open pipe, in the pipe that's open on both ends. So this one I'll call lambda 2. How many lambda 2s do we have? That's half a wavelength, and that's another half wavelength. So the full lambda 2 is equal to L, which means lambda, which I'll write as lambda 2 equals 2L over 2. So I'll make a note here. I'll say both, and I'll say only pipe, meaning that the rod doesn't get that mode. Let's go to the next one. For the next one, you have one more node in the middle. So the number of nodes in the middle show up as the subscript here. That's one node, lambda 1, two nodes, lambda 2. So now we're going to have 3 nodes. And this time you do have a node in the middle, so it also addresses the rod in this case. So that's half a melon plus a half melon, which means one wavelength plus half a wavelength, 3 halves. 3 lambda 3 over 2 will be equal to the full length of the object. And so that's lambda 3 equals 2L over 3. And this one will apply to both of them. So the general trend here is the following. For the pipe, for the open pipe, you're going to get lambda n equals 2L over n for all integers. By integers I mean positive integers like 1, 2, 3, 4 and so on. And for the rod that's clamped in the middle, you're only going to get lambda n equals 2L over n for the odd integers. Odd integers are integers like 1, 3, 5, 7 and so on. So 1 is allowed, 3 is allowed, but 2 is not allowed. So that's the summary. Once you have the wavelength for these modes, you can immediately go ahead and find the frequency using the formula known as the wave relation. So let's look at that a little bit. I'll divide the wave relation discussion into two categories. One is for solids. Rods are solids, and so you need to think of them as one category. And the second category I'll talk about, pipes are usually filled with fluids or gases. So that'll be the second category. And both these categories have a little technicality associated to them. Let's see what that is. First, let me write the wave relation. The wave relation is lambda n times Fn equals the speed of sound in that medium. The speed of sound in a solid medium is given by the formula V equal to the square root of the Young's modulus divided by the density of the material. Now, if you go back to one of the videos I had earlier, I think it was the one where the cable stretch was deduced based on the Young's modulus. So there I told you what the Young's modulus was, how it was defined and so on. Let's actually see if this gives the right units at least. The derivation is beyond the scope of this course. The Young's modulus is measured in pascals, and density is measured in mass per volume, so it's kg per cubic meter. Pascals is newtons per square meter, so I have kg per cubic meter down here. So one of the meters will survive downstairs, which will go upstairs. So I get Newton meters over kg. Now Newton meters is joules, so I get joules over kg. Now think about kinetic energy. Kinetic energy is 1/2 mv squared. If you divide 1/2 mv squared by m, which is kg, the m's will disappear, and I'll just get square root of v squared, which means I will get meters per second when I take the square root. So units work out nicely. For the gases, you're going to get, again, the wave relation, lambda n Fn equals v will tell you what kind of frequencies you're going to get. The speed of sound in a gas, though, is given by a formula that's different than this. Young's modulus, if you remember from the earlier video on stretching the cable, was defined as stress over strain. And stress itself was defined as the force per perpendicular cross-sectional area, and the strain was defined as a change in length divided by the original length. Now those are concepts that are easy to understand for a solid object, because on a solid object you can put a force that acts on its perpendicular cross-sectional area, and then you can also talk about the change in length of a solid object when it is compressed or stretched in that manner, and you can also talk about the original length of that object. For gases, all those concepts are out the window. So how do we talk about this speed of sound for gases? Well, in that case, the speed of sound is given by something called the bulk modulus divided by the density of the gas. The bulk modulus, as you may imagine, has to do with compressing the gas from all directions. So unlike a rod, you cannot just apply a force in one direction. You have to compress it in all directions using the concept of pressure. The units work out exactly the same way because bulk modulus is also defined in units of pascals, so I won't bother doing that. I'll instead spend more quality time talking about the bulk modulus itself. So the bulk modulus, for most substances, turns out to be a negative quantity, so I'm going to put absolute value signs where I need to. The bulk modulus is defined as the pressure that you apply over and above the atmospheric pressure, which results in a volume strain. And this is where I'm going to put the absolute value sign, because for most substances, when you try to compress them, like you take a bunch of cotton and you wad it up with your hands, the volume change is always going to be negative. So you don't want this negative sign to appear under the square root. That's the reason why we have this absolute value sign. So this is the definition of the bulk modulus. And you can look it up online. The bulk modulus for all kinds of substances are listed. And you can find tables. It's very sensitive to things like pressure and to temperature and humidity and things like that, whereas this is somewhat robust. So I think that I'll stop there. That's the basic theory behind rods and pipes.